Okay. So the last thing in chapter 4 is our diagnostics on a linear regression, or least squares regression. Basically, how good is our line? Do we have a good line? Do we have a bad line? How well does our line fit our data? We have our R value, which tells us a lot, but we can dig in a little more to figure out how much better, a better measure for it. So, we have open diagnostics. Least squares regression. So we talked before about our R value, so our correlation coefficient. So this time we're going to take our R value and square it. Now I'm thinking of variance. They call it the coefficient of determination. And just like our R value, it can't be larger than 1, but since we're squaring it, and even if we have a negative and we square it, it's positive, we get our R value, or R squared value rather, is between 0 and 1 this time. So of course, just like our R, the closer we are to 1, the better our data fits a line. The farther away, the less well. This tells us a kind of a percentage of, I don't want to say this, how much tells what percent relationship. And we'll do that, can be determined. The linear regression. So maybe there's a tight relationship. One probably explains the other, but maybe there's some other variables happening in here that we're not measuring that's changing our data a little bit. And honestly, most of the time there is going to be other things that mess with our data. Okay. We have a couple equations and I'll show some pictures. So our total variation, this equation is our sigma, so the sum of y minus y bar, so our individual data values minus our mean, square each one. And that's going to equal y minus right. We dealt with that before. Squared plus y hat minus y bar. Oh, that was our measured y squared. Not measured, predicted. Right, look at that. So our y hat is what we predicted based on our model. Our y bar is just the mean, as always. And then the y is just the actual y value that we measured from our original data. So 3 ways to say similar things, but are kind of different. So this piece here is our unexplained variation. The stuff that our model, or not our model, our actual data minus our model data, there's a difference there and we don't know why. So that's the unexplained part. This would be explained variation. So our model minus our mean. And we square all of those and it's going to give us a nice positive number in the end. Okay, I said slide 81, which I do believe I pulled up already, which should be here. Okay, so this is a graph. Can I zoom in a little bit? Yes, I can. Nope. Stop it. So our graph here gives us a picture of it. So our line is the line we graph. And we have our unexplained variation is the stuff above in this case, explained is below, and then our total deviation. So it just kind of gives you a picture of our data. And we always square the data values because we're going to have positives and negatives here. And if we don't do that, we're going to get positive and negative, turns into 0, doesn't tell us anything. So we square it to make sure everything's positive. Okay, and I said the next thing we need to look at is 91, but we'll get there in a sec. Okay, so, whoops, we create a residual plot. Okay, you go away. This was on slide 91. When we graph this, we want our data, or we want the plot to look like we want, like, we took a shotgun, right? That's the one with all the little different BBs, I think. Yeah. Well, we took that, shot it at here, and it's just random. If it looks like a shape, that's a bad thing. That means there's a lot of unexplained variation happening. And there's probably a way to explain it somehow. So we want this would be a good plot. So our variation is just kind of random. A bad one would be something like that. This would be bad. Because there's another model we could use for it. Those are supposed to be dots, not squigglies, but I'm not changing it. Okay. And our residual, how do we graph this? Residuals. So for each data value, the predicted, the y hat, we're going to take our actual data value minus our y hat. That's going to be our residuals. And our explanatory is the y hat minus the mean. So that's how we find these. I would recommend another spreadsheet. Plot them all out, figure out what goes where. You can just subtract each one as you go. So you'll find your y, your predicted, and you can subtract them from each other and then subtract the predicted from the mean, or vice versa. And then you plot them. So this is here. The plot on the left is a good plot. So our differences are kind of all over the board. Some of them are big, some of them are small, but they don't create a shape. The one on the right creates a shape. You can see a kind of almost parabola, but you go down and go up. That means there's probably something else going on there. A linear model is not the best measure for this. I'd have to see the data to tell you for sure what would be a better measure, but linear is not it. So this is one of the cases where random disaster is better than, you know, a shape. Usually doesn't work like that. Okay, that is the end of 4. So I'm going to stop this video and start the next one.